So let's continue. And I just got an idea what I want to cover here. I'm going to talk about arrays, but I'm going to show you a problem, solution to a problem that'll help you understand better about this prime number algorithm, prime number checking algorithm. So a lot of people are having trouble understanding the reasoning behind how we do the code for this prime number check. But there's a pattern to this that shows up several times in this course. There's going to be this sort of this logical structure that carries over and applies to many different kinds of problems. So I'm going to show you a problem that's has that same logical structure that this detecting prime number problem has. But that's we're going to solve a problem in arrays here. So let's see, we have some code to do, right? So lots of things to do here. And let's see, what I want to do is start bringing your attention to the exam. And I have some sample questions here. So let's pick out a sample question that does this challenge that I'm thinking of. Here's one. We could do this one. That has a similar logical structure to that prime number finding algorithm that you're working on. So does this one. This one has the same logical structure, and this one as well. 1, 2, and 3. All of these, and this one as well. All of these, 4 of these in a row, have the same essential structure that the prime number determination algorithm has. Does anybody want to pick one of these? 17, 18, 19, and 20. They all solve different problems. They have the same basic logical structure. It's part of the key overriding logical structure is all the same. And I want to point that out when I go to solve these. I think the easiest one to do is this one here. Well, maybe not. Maybe this one is unlucky. How about if we do that one? All right, this function here is unlucky. It returns a Boolean value. So in other words, it returns true or false. And what we do is we pass in an array A. And an array is a sequence of values. In this case, it's a sequence of ints, because we have the data type there. So A is an array or a sequence, and that's indicated by these brackets. And so A is an array of int. And then the second argument, now we have a comma here, so that's the end of the first argument. And the second argument is an integer, or int, with the name len for length. It's short for length. So this len variable contains the information about how many items are in A. So we don't know, when an array is passed in as an argument like this into a function, we don't know how many items are in the sequence. So we have to pass that information to the function separately as an integer. So that's what we're doing here. Now what the function does, there it is right there. This is the description of the problem. The name of the function is unlucky. So it tells the calling code whether A is a lucky or an unlucky array. And it's up to us. How do we want to define unlucky? I'm sorry, it's 19, not 20. I'm sorry, it's 19. This is the one here. What does it mean to be unlucky? Well, if it has the number 13 in the array anywhere, it's unlucky. It could be all 13s or just one value could be 13. Then we say the whole array is bad. And if 13 doesn't appear in the array, then it's not unlucky. So we return false. It's not unlucky. So we return true if A is unlucky. If A has a 13, return true. It's unlucky. That's why we use this verb here is unlucky. Is the data being passed in unlucky or not? All right, let's code this up. And this is similar to this prime number determination algorithm. And we can have test cases here. So we're going to implement a function, is unlucky. So let's start with a stub. Let's say it doesn't matter what is passed in. We're going to return true. We're going to say A is unlucky. This is called a stub. It's not a full implementation. It's just getting ready. It's the step one in several steps to getting to the solution. So we're doing incremental development. So what we'll need to do is have code that calls the function to test it. Is that how I describe it here? Oh, this is the exam. Yeah. The exam is actually gives. No, it doesn't have any examples. Okay. So let's create an array A that's unlucky. Okay, that array is unlucky because there's a 13 in there. So that means if we call A, and by the way, on this exam here, this is a sample exam problem. You don't need to write a main in the exam. So in the exam, you're just going to provide the implementation for the function is lucky. You don't even have to write this down on your exam paper because it's given in the problem statement. But for us in lecture and in lab and for the assignments, we're going to write a main program with some test data and check to see that our work is correct. So let's call is unlucky. We're going to pass in A, and then we're going to pass in the length. What's the length of A? It's 6. There's 6 items. Now, is unlucky resolves to true or false. Here it'll resolve to true, so we could print it. I'll do it like, it'll come out, it'll print as a 1 actually. What's going on there? We don't need this stuff. And is unlucky, return true. Oh, this is C++11. What about this? So let me say, so those are both valid syntaxes. So the initialization that I'm using here requires C++ 11, yeah.
Would you need to put the header pound include vector when using an array?
The header for what?
For vector?
No, we don't need that. Yeah. So if we put it in there, will it fix this problem? No, I don't think so. Let's test it. Okay. There's always one way to test it, right? So we're not working with a vector. Warning. It's only available in C++ 11. And by the way, we don't need this in there. It's the same error message. So the standard is C++ 11. So we can use that initialization code in this case. And when we run the program, it says 1. That's because in C++, it's designed to be as compatible as possible with C. And in C, Boolean values are represented by integers. False is a 0. All other integers are true. But by convention, I guess they're using a 1 here for true. But you could use 2 and it would also be considered true. Anything that's not 0. So only 0 is false. And that's a detail that is hidden from most languages, by the way. You know, in other languages, when we print out the return value of a function that's a bool, it'll print true. It'll print TRUE or false. But in C++, it won't do that. So if we wanted to do it like that, we could do it like this. So if is unlucky returns true, then we will print true. Else we're going to print false. We can do it like that. Now it's going to print true for us. If we change our stub to return false, of course, we're going to get false. Let's see if I can make the font larger in the console area. Does anyone know how to do that? Oh, look at that. Look at that. All right, that's good. Is that big enough? Yeah.
How do you got first true and then false?
How did I what?
How do you got first true and then you got false? I mean, the code is same, right? So the first output is true and then another.
So you're not talking about preferences, right? So you're talking about
Yeah.
why does it print true?
No. In the terminal.
Yeah.
When we run the program.
It prints false. Because we're returning false. It doesn't matter what A is.
Oh, okay. Yeah.
I'm playing around with the stub. Okay, we haven't solved the problem yet. This is step 1. We have a running prototype. There's another way to do this, which is what you'll do in the exercises. You're going to use assert. So there's a header file for this. C assert. And this is just for the test code. We're going to assert that is unlucky returns true. And then that's a test. And then we're going to print all tests passed. All right, let's switch this back to true, because that is unlucky. So we create our test data here. We define an array A with 6 integers in it. One of them is a 13, so it's unlucky. And then we call the function here. And the function should return true. And well, of course it does. We force it to return true because we're still developing test code. We haven't even started to work on the algorithm. We're not even thinking about the algorithm. We're just working on writing test code. And by the way, this is an important strategy called, what's it called? Test-driven development, right? Remember that term, test-driven development. When you go to interview for a job, use that phrase. That'll help. Because it's a newish sort of approach that developers are talking about and try to follow. So test-driven development. Write your test code first, and then do the implementation of the target system, and then you write your automated test code against it to check how you're doing. So that's what we're doing. We're writing our test code first. So is unlucky should return true. When I say return true, it should evaluate to true. Okay? When I say return true, I mean evaluates to true. What do I mean by evaluate to true? That's what I mean by I take what's highlighted there and I replace it with either true or false, the value that's returned, in this case true. It's the same thing, if like you look in math, if I go, it's 3 plus 4, that expression evaluates to 7, right? That's the same thing. This expression evaluates to true. That's the same idea there. That's what it means for a function to return something. You could think of this as a function that's returning 7. What's the function here? The function, this is the addition function right here. The addition function is returning 7 for this case. In other words, this expression evaluates to 7. This function returns true in this case. It evaluates to true in this case. So that's how you look at it. Now you don't really need to say equals true here. You can just do this, because is unlucky returns true or false. So we're just asserting that it returns true. But it's up to you. Some people like to see it like that. It reads better for them. No, it's up to you what you want to do there. So we'll have multiple test cases here. And all the test cases will have to pass. All the assertions will have to silently complete without halting the program. And then we come to the final line, which prints all tests passed. Let's see it work. All tests passed. We passed all the tests. Well, let's create another test. So we want our tests to be exhaustive, or not exhaustive, sorry. We want them to be representative of all possible special cases. Let's create a whole bunch of test cases here. Let's put the 13 in the first spot. Maybe that makes a difference. And this is an array of size 4. This is also unlucky when it's array B here. Should be B. This is our test code. Let's create another array C. In this case, we'll put, it'll be all 13s. Well, nah, maybe not. Maybe we'll put it a 13 in the last spot. So C should be unlucky as well. Let's create another test case where the 13 well, there is no 13 in there. So this test case returns false. So C, that should be D rather. D is not unlucky. D is lucky. Well, it's not lucky. It's just, it's not unlucky. So that's D. All right. And maybe being lucky is something else. Maybe you need a 7 to be lucky. Yeah.
So we can choose any numbers.
You can choose any numbers, but you don't want to just choose any numbers. You want to choose numbers deliberately to test edge cases, special cases. Like this is an edge case. The 13 appears in the first spot. Here's another edge case. The 13 appears in the last spot. Here's like a normal case, not an edge case. It's the 13 is somewhere in the middle. What happens? We'll have some kind of loop, see? But what happens if the loop doesn't make it to the end? So it never reads that 13. So we're testing for that. That's called an edge case. And for unlucky, so anyway, that's what I'm doing there. So these 3 cases return true, and then the 4th case returns false. And then all of those should pass. Of course they don't, because we always return true. We still have a stub. It's called a stub code. We haven't even started implementing the algorithm we need yet. So let's see. Assertion is unlucky failed. And what line did it fail in? Line 25. I have it highlighted right there. Line 25. Does everyone see line 25 right there? Is unlucky should evaluate to false, but it does not. Evaluates to true. So that means our implementation of is unlucky is not correct, which we know in advance. We're just returning true always. But now we've got all our test code written. So we're ready to go. We could add more tests if we want to, right? Like an array of size 1, maybe, whatever. All right, so how do we test this? Let's think about it. Well, how would you do this? Yeah.
With a for loop?
A for loop is ideal because we know exactly how many slots are in the array, and that's how many places we have to look. In the worst case. In the best case, we'll have to look at the first slot, find a 13, and say, it's unlucky. We don't have to look any further. That's the best case. The worst case is D here, which is there is no 13, so we have to look at the first spot, the second spot, third spot, fourth spot. And we looked at all the spots. None of them are 13. Now we can conclude it is not unlucky. Return a false. So in the worst case, we have to scan the entire array. And in fact, in the best case, we're going to start the process of scanning as well. So a for loop is ideal. So we'll start at position 0. Remember, array positions start at 0. This is position 0. The first position is position 0. And then I is less than something, and plus plus I. And then we're going to do something in here. So what goes there? Someone else? Anybody?
Size?
Yeah, but look at the code. Where is size? What variable represents size? Remember the LEN? That's short for length. That's the number of elements in A. That's a typical abbreviation for length. Length is used. We could have also said size here. We could have done that. That's also all right. It's just that old code, you see this a lot. So I just use LEN there. But size is good too. Size may be more clear. But just to get used to LEN, because you might see it later on, I'll use that. Now, do we want I? So, we have strictly less than here, right? But we could also have less than or equal to if we want I to hit LEN. So we got to think about that. Now, what do? What goes in here? What are we checking for? So I is going to start at 0, then it's going to go to 1, then it's going to go to 2, right? So for each value that I takes on, what do? We check to see if the number in the ith position is a 13. So in not the ith position, in position I. This is position. What position is that? What position number is that? Yeah, 2. This is position 2. The third position is position 2. So when I is 2, we do not find a 13. But when I is 3, this is position 3. Remember, position start at 0. 0, 1, 2, 3. When I is 3, we find a 13. And so we know, oh, it's unlucky. We don't have to look at position 4 or 5. We don't need to look there because we found a 13. We're done. See, that's the same logic as that prime number determination algorithm. We look at every divisor. We start at 2. Does 2 evenly divide the number? No. Does 3 evenly divide the number? No. Does 4 evenly divide the number? No. Does 5 evenly divide the number? Yes. Oh, 5 evenly divides the number. Then it's not prime. We don't have to, even though the number is 25, we don't have to check 6, 7, 8. No, we don't have to look anymore. We found a divisor. We're finished. We can terminate the loop. We don't have to keep checking numbers anymore. See, it's the same logic. We found a 13. We don't have to keep checking numbers anymore. All we had to do is find 1. You see the similarity? This similarity, this structure here will recur. As I showed you in the example problems, all 4 of those problems have exactly this architecture to it, this logical structure. So you got to grasp this. So if the value at I is a 13, then we're done. It's unlucky. It's unlucky. So if A of I is 13, we return true. Now, when we return true, what we do is we exit the loop. We don't do this either. We don't do the line after the loop. We exit the loop and we return from the function. See, return means let's get out of here. We're out right now. We're not going to do anything else. We're not going to finish the loop. We're not going to do the statement after the loop. We're just getting out right now. And we're evaluating to true. So this is one way to break a loop. There's other ways as well. We'll see those later. Now, this isn't going to work. So when do we return false? When do to return false, we have to know that no value in A is a 13. That means we want the loop to finish without returning. So this is the point in the code right here in line 14. That's the point where we finished the loop and we have not returned. We have not exited the function with that return statement. And so at this point, we know there is no 13. We did not find a 13. So it's not unlucky. We're going to return false. Now, this assertion should succeed. This assertion should silently complete without complaining, which means the program reaches this point. Is if our assertion here was failing, and so we terminated right there on line 28. We never printed all tests passed. Now line 28 will not halt. We'll get to line 30, and the program will say all tests passed. All tests passed. There it is. Oh, and I had the test case. We don't need to list the test cases here because they're coded in right there. Lots of test cases. Anyway, that's that. So a lot of your code is going to look like this in coming assignments. You'll have test cases to use and so on. Any questions about this one? This is super important. You got to get this. You got to practice this. Go back and do all these other ones in there. Did the question over there?
You know when you put two equal signs?
Yeah.
How does that not set it to true? Because like when I tried doing the prime testing program, it would set it to that number when I put two.
Oh, you used a 1 equal sign. 1 equal sign sets it. Of course, you can't set this if you can't set a function, but yeah, 1 equal sign means assignment. 2 equal signs means comparison. So they're two different operations. They use the same symbol, but a comparison uses two of that symbol. Yeah. So if you look at your code, you'll see you use a single equal sign. That sets it. A double equal sign won't set anything. All right, let's look at this exam one a little more. What else did I want to talk about? Wait a minute. So here, character sequences and pointers. We're a little far from the exam. Maybe let's do one more exam problem. Let's do this one here. Okay. So what does this code print? So this is a sample exam problem. This is a problem I gave on an exam in the past. It gives a block of code here, figure 1. It says when that code runs, what gets printed? Let's look at that. You see how I shifted that out so fast? Do you know how I did that? I just highlighted it and hit, this is Shift Tab and this is Tab. That's very convenient. So I just highlighted everything and hit Tab. Put tabs in there. What does this code print? Now on the exam, you won't have a computer to test it. So you have to reason about it. How do we do that? Basically, this is an exercise in reading code and maybe analyzing code. How do you read code? Look at the statements in main, okay? I just highlighted the code inside main, right? No, there's statements and there's statements within statements, right? Statements within statements. Statements within statements within statements. It can be infinite. Well, not infinite, but it's arbitrarily deep, nested. So when I say top level statement, it's not, how many statements are direct children of in this code block that defines main. How many statements are top level statements in main? When you see that, when you look at that, count them. How many statements do you count? They're top level, not statements within statements. How many top level statements do you see there? You should be able to count it, right? What do you see? There's two statements. Two statements. This is the first statement. It's a declaration and assignment of I, initialization of I. And this is the second statement. Loops are statements. They're just it's one statement. Well, it has substatements, though. But at this level, it's one thing. You're one person. If you dig inside, you'll find, well, there's a heart, there's lungs, there's a kidney, and there's a liver. But no, we're not looking at that level. We're looking at that whole holistic level. We're looking at this level. And so here, when we look at it from that level, we just see one statement there. And this is really important. You got to know how to organize, what you're looking at. The first statement runs and completes, and then the second statement runs and completes. That's how you look at it. Now the loop has substatements within it. These are the substatements. There's two substatements in this while loop, and they will run repeatedly until the loop condition right there becomes false. So the while loop will repeat its substatements after evaluating its loop condition, and after evaluating the loop condition to true. It'll keep evaluating the loop condition, run the substatements, evaluate the loop condition, run the substatements, as long as the loop condition is true. As soon as the loop condition is false, when I less than 27 becomes false, we do not execute the substatements. We finish. We've completed the while loop statement. While loop statement finishes, and we go to the next statement. So now we have three statements. We initialize I, we complete the while loop, we complete the initialization of I, we complete the while loop, and then we complete this output operation. So now we have three top-level statements. When you look at the loop, once again, the substatements are repeated after the loop condition is evaluated to true. And we just keep trying the loop condition until it comes false. When the loop condition is false, then the loop statement is done, and we go to the next statement. You got it? That's how you step through it. That's how you become a computer and execute the code in your head. All right, so let's look at it. Let's walk through it. I'm going to start here. Okay, I is set to 3. All right. Maybe I'll just make a little note here that I is currently 3. I'll just put a colon there. I is 3. There's only one variable, so that's easy to keep track of that. So now what's the next thing? After we do that, now the next thing we do is we have to do this while loop. Well, how do we do the while loop? It's not one operation. It's lots of little operations. And what's the first operation? It's not going to be that, right? That's not the first thing we do when we start the while loop. It's not that either. That's not the first thing that we do. The first thing that we do is we evaluate the loop condition. That's the first thing we do. Now, if the loop condition is false, like let's suppose that was our code, all right? That means when we start the while loop, the loop condition is false from the get-go. Well, that means if the loop condition is false, it means we're finished the loop. We've completed the loop statement. We haven't even executed the substatements. They don't get run. And then we say done. That's all we do. We just print done there. But the problem in the exam exercise is to start with I equaling 3. So when we execute the loop, as the first thing we do in that execution is to evaluate the loop condition. I is 3. 3 is less than 27, so the loop condition is true. If the loop condition is true, it means we need to execute the substatements. Let's execute the first substatement. Now, by the way, there's like things within things within things, right? So when you look at that line 12, that first substatement fits on one line, line 12. We could stretch it out, by the way. It doesn't have to be. That's valid right there. That's the same. Gives the same result because the line the statement ends at that semicolon. So we could spread things out. We can't do that. That won't work. All right. We got to keep E and DL together. Well, we could do this. That's the same thing right there. That's equivalent. The compiler will see this as one statement right there. It'll block that all together and say that's my one statement. Backing out of that. There we go. All right, so the loop condition is true. I is currently 3 here. I made a mental note of it there. Well, not a mental note. I made a written note. I is 3. The loop condition is true. And so we're going to start by running the first substatement, then we'll run the second substatement. But look at the first substatement. We can't just do the whole thing and then go to the next one because it's got pieces in it. It has operators in there. It has 3 operations. It has an output operation here. It has an addition operation there. And it has another output operation there. So you got to do these one after another. They're not all done at one time. You do them sequentially. So which one runs first? Well, this addition has higher precedence than output operations. So we do that first. We evaluate this. This is not a statement. That's not what I have highlighted there is not called a substatement. It's not a substatement. It's an expression. The statements are composed of expressions. You can have expressions within expressions. Here, this is an expression. How am I doing on time there? I'm eating up the whole time. So this is an expression. And we're going to evaluate this expression. So that expression evaluates to 4, because I is 3. So we'll just do it like that, see? So I plus 1 becomes 4. And now this is in the process of executing this statement, we're going to go through these state transitions. So we've just evaluated this addition operation. Now we have a 4. Now what do? We have 2 operations left to do. We have this output operation and that output operation. Most output operations, as most operations do, not all of them, but most of them are evaluated from left to right. So we do the first output operation first. And then we do the second output operation after that. So this output operation, you have to have a left-hand side and right-hand side. It's called a binary operator. It's like addition. This is a binary operator. Binary means 2. There's 2 arguments. There's an I and a 1 there. There's a left-hand side and a right-hand side of that plus sign. Here we've got a left-hand side, which is C out, and a right-hand side, which is 4. So now we're going to evaluate this expression that I have highlighted there. What does this, see, this is a little tricky because this operation, this output operator, evaluates to something. This expression evaluates to C out, but it has a side effect. It prints 4 into the display. It sends 4 into the standard output stream, which we're running it as the console. So this expression, when this output operation runs, we print 4. And the expression itself evaluates to something. What does this expression evaluate to? The printing of 4 is one thing. That's a separate, kind of process. We're printing 4 to the console, but now the expression evaluates to something, just like this expression evaluated to 4. This didn't print anything. All that expression did was to evaluate to something. It had no side effect. But this operation has a side effect. It causes 4 to go into the standard output stream. But then the expression itself evaluates. What does it evaluate to? Does anyone know? I said it, but maybe you didn't catch it. That expression I have highlighted there evaluates to, the output operator evaluates to its left-hand side. The output operator evaluates to its left-hand side. You get that? That's a simple statement, right? The output operator evaluates to its left-hand argument. So what do I replace what I have highlighted with? I'm going to see, this is line 12 shows me the first stage of evaluation. Line 13, what goes into line 14? What am I going to show that the above thing evaluates to? What am I going to write next in the stage of sort of simplification as we proceed through this expressions that comprise this statement? Wait, let me tell you again. This is the output operator. The output operator evaluates to its left-hand side. What do I put there? Huh? 4? Is 4 the, no, 4 is the right-hand side. The operator evaluates to its left-hand side. What do I put there? Simple, right? Someone's got to say it. See out. See out's the left-hand side, right? I said it. The output operator evaluates to its left-hand side. It evaluates to see out. So this becomes see out. And then this has not run yet. Because that's last, because we're doing left to right evaluation. So this is where it goes. It starts here, then it becomes this, and then it becomes this. We have now when we evaluate line 14, what do we do? When we run this expression, the final kind of operation, we're going to print a new line into the output stream, which appears on the console, and you'll see the prompt will come up under there. And after we print a new line, this expression evaluates to the left-hand side of this output operator. So this evaluates to see out. But you know what? That's just discarded. I mean, that's not used anymore, right? It's just evaluated. So it's evaluated to you out, but it's not used. We could write it like that if we want, but I'm trying to show you the stages. 1, 2, 3. These are the stages of how that statement is evaluated. You got to pick this up. This is the thinking process. I'm going through this really slowly so you get this. You got to get this. This is how you read code. Not always. I mean, you got to start reading code like this carefully. And then later, you're going to get faster at it. You'll glance at the statement and bam, you'll see holistically that, oh, I know what's going on there. But you can't get to that point until you practice this minutiae analysis that I'm doing right now. So you've got to understand how this works. So this will print 4. All right, that prints 4. And a new line. So that's going to print, it'll print a 4, and then a new line. It'll look like that, okay? And then after this statement completes, we do the next statement. How many operations are in that statement? Am I running out of time? No. There's 2 operations. There's assignment, which is a single equal sign. It's not a double equal sign, that's comparison. And then there's multiplication. Which operation goes first? Here, in this line, the addition goes first. In this line, what do we do first? Assignment or multiplication? I do multiplication first. That has higher precedence. So this substatement is evaluated to something, and it becomes the right-hand side of an assignment operation. So let's do the same analysis we did with the other one. So this is the first state, and then in the second state, we have I equals, what does this evaluate to right now, huh? 1? I times 3. 9. Because I was initialized to 3. This is where we're keeping track of the I right here. We did not, look, this did not modify I. This expression uses I. It does not modify I. We're reading I. The expression reads I. And it adds it to 1, and that thing evaluates to 4. This assignment, this is where we modify I. So we need a type of assignment to modify I. So this evaluates to 3. So this expression evaluates to 9. And now we do the second operation, which is assignment. That means I, which represents a memory location in RAM. And that number in RAM now changes. It's no longer representing a 3. It is now representing a 9. And by the way, this also evaluates to something. This evaluates to, what do you think that evaluates to? Any guesses? I think it evaluates to 9. I'm pretty sure it evaluates to 9, okay? Just like this evaluates to C out at the end of the day. But it doesn't matter. This is just discarded. That's not really looked at. All right, so that's good. There it is. So we printed 4 here, and then I became 9. Now what do we do? What's the next thing we do?
Wouldn't we run it again for 4 rows?
Huh?
Would we run it again for the next?
Yeah, run the loop again. What do you do next to run the loop again? Huh?
The loop's going to be start with the 9 and runs again till is less than 27.
Yeah, so what do I do next? What do I evaluate next?
The loop condition.
The loop condition, good. That's what we do next. We evaluate the loop condition. If the loop condition is true, we'll execute the body of the loop. if the loop condition is false, the loop is done. We go to line 15. So is the loop condition true or false? True. And we made a note here. I is 9. 9 is less than 27. So that means we go to the next line. What do we print? We print 10. Okay, I'm going to put it down here. We also print a new line, right? So I'm just going to show it like that. So we did this just prints 10. This does not modify I. Very important. There's no assignment to I. We're modifying the output stream. That's what's getting modified here. We're modifying the output stream. What about this line? What happens here? What's the result of this? Yeah, so 27 gets stored into I. Because I is 9, 9 times 3 is 27, and then we assign it into I. I becomes 27. What do we do next? Don't go too fast. I want to know the little step. What's the little step we do next? Huh?
It will not run anymore. It will output will be done because the 27.
I don't want a global thing. I want you to tell me just a little bit of sand here. What do we do next?
Evaluate
Look,
the
let's
condition.
send it back into us.
The loop condition. Yeah. Now, so you're giving me the forest, and I just want a tree here, okay? But you do need to think about the forest as well. But the problem that students have is not thinking about the forest. You're normally, by default, you're in forest mode. You look up there and you see all the code all at once, right? You're not looking at a semicolon. You're looking at the whole thing, the whole painting. You're not looking at a forest in the paint, at a tree in the painting, or a brush stroke in the painting. I'm trying to get you to look at the brush strokes in the painting like an art expert would do. You got to operate at that level to grasp, to get good at this stuff. All right, so there's the loop condition. I less than 27. Is the loop condition true or false? Does it evaluate to true or false?
False.
False, good, because that's a strictly less than. The loop condition is false. So that means the loop statement is finished. We don't do the substatements. We go to the next line. We print done. So we're going to print done now. Now there's the exam problem right there. And imagine yourself in the exam. You got to practice this. You know, we're like coding and running it. That's not the best way to practice it. The best way to practice it is to figure it out on paper first, as if you were sitting in the exam, because that's what you'll be expected to do. And then after you do that, maybe you can go ahead and do this to check the answer, to find the answer, and to practice programming as well. So the answer to this, you would write 4 and 10. Actually, you know what? I probably would get rid of that E and DL there. Yeah, we don't need that. That's just maybe, some students, they would, a really clever student, they would, if I didn't put this blank in there, they would put, 410 without any space between them. It would be 410. So I'll put a space in there. But I don't want to throw off people, so I would just do that, and you can just put the space in there. I just want to see that you can analyze the loop there. All right, so that's that. We just made a little change there. Check the time again. So here's another problem. What does this print? Here's another problem. What does that print? So you got to practice these. What does this print? And I was just showing you how to read the code, how to break it down, how to break the painting down into brush strokes, which brush stroke to look at first, which one to look at next. You got to get down to that level. You can't just look at it and say, oh yeah, and just extract the number somehow. It doesn't work. You got to dig into the details and understand how expressions are evaluated, what's their order, How do they influence things around them? Here's another one. What does this print? What does this print? And then we've got some other kinds of problems here. You know, write code that does something. Write code that does something. Here's another section of stuff. Show the Unix command to display your current location in the file system. That's why, you know, I want you to practice. That's PWD, by the way. That's my current location in the file system. And I can make a directory called basics, say. I do ls to see where I'm at. Then I can cd in the basics, ls. I want to look at my parent, ls dot dot. I can look at my parent. Okay, that's, I go to my home directory, it's just cd, enter. Oh, I need to be in my workspace, check it. There I am again. You need to practice that because that'll appear on the exam. Of course, the reason it's on the exam is it's important. Right? This command line stuff is essential. You got to know how to do this. If you want to progress through the computer science program, if you're not in the computer science program, you may not need to know how to use the command line, but there's a good chance you do actually. And that's why you're in here. That's why your major requires you to be here. It's important to understand the command line interface. And then after this stuff about Unix commands, then there's a bunch of questions about, oh, here's a function, implement that function. Here's a function with arrays, implement that. Implement, all of these, lots of those. And here's write a program, guess the number game. Look at this. This is straight from your assignment. This is problem 1. Implement, guess the number game. That's problem 1 of the next assignment. What's it called? Algorithms, the 3rd assignment. So I just dropped a problem right out of your assignments right into the exam. I don't want you to be surprised on the exam. It's very clear what you need to learn to do here, what you need to practice. It doesn't have to do with memorize. You got to memorize a little bit. You know, you have to know that. You know, you have to remember that double equal sign is comparison. Single equal sign is assignment. You got to memorize that, yeah. But that's not good enough. You got to practice. You know, it's like learning how to play the guitar. You got to practice it. You can't just read a book about it. You got to practice it. Any questions? That's it? That's it for today then.